noises even they're like a meter away. So I really
If you
recommend
insist.
it.
If you insist, Andrei, I will do that.
No. You if you don't have any ambient noises, that's fine.
And I close the door, so the ambient noises
Okay.
should be minimal. And if there is a lawnmower outside, nothing will help.
Actually, without the headset was better, I think.
Well, I haven't turned on the headset yet, so what do you think? So very important.
Okay. As always, we'll wait a couple of minutes.
Yeah.
We still have 1 minute to 5, by the way.
Yeah, so,
Really? Oh, okay. So you insist me to be
okay.
just sharp?
Better now?
Yeah, that's fine.
Okay, so is this better?
No, it's either way. So it's
It doesn't
okay.
make any difference to me. Okay. So let's try this. Okay. So hopefully you can also see my screen, but I don't know whether that's true.
You can see your screen.
But I think it's better to compress the size a little bit.
Compress in what sense? What do you want?
In the sense that,
A bit smaller because it doesn't fit into this. Now it's better. Okay, now you can see the title. The question is a little misleading.
Hmm?
Okay. I'm just. Andy, what do you think? Shall we start?
well, why not? If you ask me.
I don't know why.
There is another Andrei sitting under the Christmas tree already. He has started. Just on my screen.
we had this tree since the day after Thanksgiving, so it's so for a couple of weeks now.
It's all New York tradition to have Christmas tree bazaar market next day after the Thanksgiving.
Yeah.
Even COVID cannot change it. Okay, Sam.
Yeah.
Your floors.
Okay. So this is a very belated remote birthday talk for Igor, as you can probably tell. So the talk will be still about math and not so much about Igor, because I think that's a math seminar, and hopefully we will have an occasion to have a talk about Igor in person at some point. So what I was going to do was to give a sort of panoramic talk with not so much in terms of proofs, but with some survey as I see it, so it's very biased, of course, on some questions on curves and differentials. So MG for me will be the moduli space of a genus G compact Riemann surfaces. Whether you call them Riemann surfaces or complex algebraic curves, doesn't matter, it's still the same space. And I will always write a curve as X. Okay. And then the second main object will be the Hodge vector bundle. So it's HG, it's a bundle over MG, which is a complex rank G vector bundle. So over a curve, you consider the space of all holomorphic one forms. And there is a G-dimensional complex space of holomorphic one forms on any genus G Riemann surface. So it's a rank G complex vector bundle. At some point, we'll talk about meromorphic forms, but let's not worry about it. And I will always write a form as omega. And this is just so that you know what I mean when I write X. That's always a curve of genus G, which is always fixed, usually more than 2, so that we don't worry about things. And then you can ask very fundamental questions about curves or fundamental questions about differentials. So here is a fundamental question on curves. So the question is the following: when does X have a rank R bundle, sorry, has a degree, let's do the simplest version, have a degree D line bundle with R sections, well, R plus 1 really sections, so the projectivized R. Okay, so this is a question which has the name of Brill-Nurse theory. So you can ask whether a given curve of genus 5 has a degree 7 bundle with 10 sections. I didn't think about the numbers beforehand, so the question I just asked is probably not very interesting. But the point is, in general, what you expect is there are the following situations. It could be that every curve of a given genus has...
Sam, do you mean with R plus 1 linearly independent sections?
So the dimension of, so a line bundle L such that the dimension of H naught X L is equal to R plus 1. That's what I mean. Okay, so I mean linearly independent sections. Sorry, I was speaking as an algebraic geometry. And the degree of L as a line bundle on a curve is D. Okay, and a lot is known about this question. So you can ask, for example, for which G, D, and R does such a curve, does every curve of genus G have a degree D line bundle with R plus 1 sections? That is understood. You can also ask finer questions. If every curve of genus G has such a line bundle, how many line bundles does it have? What is the dimension of the space of line bundles of degree D on the curve of genus G, which have R plus 1 questions? That's also understood generically. But for example, already if you ask a question in the situation when not every curve of genus G has such a line bundle, things become interesting. So you can imagine that there is some number, and indeed there is such a number called the Brill-Nurse number, such that this number is sort of the expected dimension of the space of such bundles on the generic curve of degree D, of a genus G. And if this number is non-negative, then indeed it has been proven that a generic curve will have such a line bundle. If this number is negative, then you would expect that only some very special curves have some such line bundles. And then you can ask to characterize these curves, you can ask to compute the codimension in MG of the locus of such curves. And if I start asking in that generality, that immediately becomes unknown. So some things are unknown. I'm not saying that there are hundreds of papers in this direction. But in full generality, the question is unknown. So that's one, in some sense, very fundamental question on curves you can consider. There are also fundamental questions on moduli of curves. So you can ask, for example, what is the cohomology of the moduli space? That's a very wide question. A lot is known. Thousands of papers have been written. In general, that's of course not known. What you can also ask is, can you say something about, well, birational geometry? So if you are an algebraic geometer, you would probably ask about birational geometry of MG. And this is to say, we would like to understand something about the Kadeira dimension, maybe about effective divisors, maybe about Neff divisors, and so on and so forth, and maybe about minimal models. And there is a whole host of questions you can ask, which is sort of trying to ask to capture the geometry of the moduli space as a whole. Is it like a projective space, or is it very far from being a projective space, meaning is it a general type variety? A general type variety essentially means that you cannot parameterize it in any reasonable way, and it's going to be hard to study. So you can ask questions about birational geometry, you can ask questions about complete or compact subvarieties of MG, what kinds there are, what kinds there are not, and so on and so forth. So these are somehow broad questions about moduli of curves. You can try to ask similar questions about moduli of differentials, but perhaps they're not so interesting, because after all, moduli of differentials is just a rank G complex vector bundle over MG. So somehow the algebraic geometry of that is not very exciting, because it's fully controlled by the algebraic geometry of the moduli space of curves. So you probably don't want to ask questions in that direction. However, if you're thinking about questions on curves, many of them are, or at least can be phrased in terms of differentials. There are many interesting questions about differentials. So you can ask, when does there exist a differential in a curve that has some properties? Or when does there exist a collection of differentials of curves that have certain properties? And this is interesting. And there are ways to approach these things, but the first approach I want to mention is complexifications. So even though we started with a moduli space of smooth genus G complex curves, and the questions I tried to list are all about smooth curves, no degenerations whatsoever, the first breakthroughs in Brill-Noether theory in trying to understand the behavior of bundles, of line bundles on curves, well, not the first breakthroughs, but sort of the significant breakthroughs in the more recent times have come from understanding degenerations. So what is this about? So you take a smooth Riemann surface of genus G and you want to understand the question on it. And maybe you want to understand the question on a generic genus G Riemann surface. So you take an arbitrary Riemann surface, and you can also determine what happens if you perturb it or if you deform it. And what you can try to do is you can break the Riemann surface. So you can make a nodal. That's the simplest case. You can make a node. So that's two complex lines intersecting in C2. And then you break things. And then when you break things and break them further on, eventually the geometry will disappear and you will be left with some combinatorics. And then if your original geometric question, you could somehow phrase in terms of a combinatorial question, you can have a hope of understanding it. And that's why the complexification is so exciting. So the complexification of the moduli of curves is mg bar. Something what was horrible happened with my pen. So mg bar. This is a so-called Deligne-Mumford complexification. And this is a complexification that is, I think, 60 years old now. No, probably 50 years, sorry, 50 years old. And this has influenced a lot of the development of the theory. So many of the results obtained on understanding curves and moduli are obtained using understanding the complexifications, because this allows you to degenerate geometric questions into questions of a more combinatorial nature, which can then be approached. Let me now say something about questions on differentials. So why do people in dynamics care about differentials? Is because there is an SL2R action, or really GL2R. So let's write GL2 to be precise, GL2R, maybe plus, action on the Hodge bundle minus the zero section. So let me describe it in words and not write it very precisely. So suppose you are given the Riemann surface and the differential omega on it, a holomorphic one-form omega. And you want to act on this by an element of GL2R, so a 2x2 real matrix. What are you going to do? You have a differential omega at every point on your Riemann surface. Locally, you can always write omega as dz away from the zeros of omega. So locally, at every point where omega does not have a zero, you can write omega as dz, where z is some coordinate, which you can choose up to translating. So if you want the coordinate to be centered at a given point, there is a unique such coordinate. So sort of what this means is that on the Riemann surface, the data of a differential is the same as locally at every point, except zeros. The data of a coordinate z, such as differential, looks just like omega is dz. So now I have a complex coordinate z, and I have an element on the GL2R. Well, z is a complex number, which I can think of as a pair of real numbers. So I can act on z by the element of GL2R. I'll get a new coordinate, which is no longer holomorphic with respect to the original coordinate z, but it's a new local coordinate on the Riemann surface. And I'll take d of that. So I'll take d of gamma z, if you wish. And I'll declare this to be gamma acting on omega. So this is the action of GL2R, which is defined, so that's a new form on the same Riemann surface, defined away from the zeros of omega, where you have to deal with it carefully. But the claim is that then there exists a unique structure of a Riemann surface. There exists a unique complex structure on the same underlying smooth surface, such as this is a new holomorphic form. So this defines an action of GL2R on the Hodge bundle by taking an accent omega and slanting, if you wish, omega, and declaring this to be the new holomorphic form. And the main question here is to classify orbits. Of this action. Well, really not the orbits, but the closures, the topological closures of orbits. And you can imagine that an approach here would also be compactifications. Somehow these orbits will never be compact, and you can try to understand what the orbits may look like by trying to understand their boundaries. So these are some questions which somehow unite curves and differentials. And there is also some work that Igor and I have done, which somehow aims to use differentials to understand the geometry of the curves, of the moduli space of curves without a differential, as I'll also describe. Okay, any questions so far? So I also don't know what the background is, so if I'm saying something which is too trivial, please tell me. Usually in the audience, people would start yawning and I would be able to see that, but here I cannot see the yawns so well.
Sorry, may I ask?
Sure.
I joined a little bit later. I didn't get, are we acting by the group GL2R on the infinite dimensional space of forms or on holomorphic forms?
No, well, we only have holomorphic forms. The only situation I deal with, we only have holomorphic forms. In a second, the forms will become meromorphic, but I never consider just smooth forms.
All right.
So we're just acting on the space. So Hg is a complex rank G vector bundle of curves with a holomorphic 1 form. And given a non-zero holomorphic 1 form, I can slant it and declare it to be a new holomorphic form. And this will be an action of GL2R. Okay?
Thank you. Thank you.
Okay. If you want to do some computations, it would be interesting to try to think about local coordinates. So you can ask, do you have local coordinates on MG? So what is MG? So MG is the moduli space of curves. So I somehow have to have local coordinates. So I need to be able to tell you how to deform curves. So there are various local coordinates on MG. You can take a small disk on a Riemann surface, take the complex structure on that disk, remove that disk, do something funny with the complex structure on that disk, shift it, have a biholomorphism, have a smooth map of the disk to another disk, and then glue the disk back in. And this gives rise to what are known as Schiffer variations. And I will not say anything about that, but what you should think of is some kind of local surgery procedure that cuts out a small holomorphic disk and glues it back in with somehow a different complex structure. And such Schiffer variations do give local coordinates on the moduli space of curves. But they are not so easy to describe, and so they're somehow highly transcendental. You're not doing some nice algebraic procedure. Another thing you can do is you can imagine that if you have a Riemann surface, you're going to glue it together from pairs of pens. So you're going to maybe cut it up into what are called pairs of pens. And then you will declare that you just have to record how you've glued, and you'll have to recall what pairs of pens you've glued. And these are called Fancl Nielsen coordinates. So they are the coordinates that just tell you, I'm going to take that pair of pens. So a pair of pens is just a sphere with 3 holes geodesically. And then you can say which one. So the length of the holes will determine that thing. And then you say how you glue them. And this will give you some local coordinates on the moduli space of curves, which are real analytic local coordinates. And then you also have some what are called plumbing coordinates. Near the boundary of the Deligne-Manfred compactification. So these are somehow things that tell you that if you have a node, so the node looks like x, y is equal to 0, you can perturb it to make it x, y equal to t. So these are pictures in C2. So x, y is equal to 0 is a node. So these are 2 branches of the curve intersection, and x, y equal to t. And I'll draw it this way, but I mean, you should really imagine that this is a smooth surface. So this is somehow coordinates that are transverse to the boundary of the Deligne-Mumford complexification. These are nice because they're complex coordinates, unlike Fancl Nielsen coordinates, which are sort of real analytic. So the message of the story here is that you can have many different ways, and there are many more, to try to construct local coordinates on the moduli space of curves, but there is no easy choice. And somehow constructing interesting coordinates on moduli space of curves is not so easy. And you would expect that whenever you have local coordinates on moduli space of curves, maybe you can get something interesting from that. Okay, let's now think about local coordinates on the Hodge bundle. And I have to say, now I'll say it once and I will not say it again. When I talk about the Hodge bundle, oftentimes I really mean the projectivized Hodge bundle. So oftentimes I really want the differentials up to scaling by a complex number. I will be very, very sloppy with that. And please ignore this because it can be said correctly, but I don't want to bother with this talk. So now you can ask, if I have a Riemann surface and a holomorphic one form on it, what kind of coordinates can I define for this space? And of course, you can just say, well, that's easy. The moduli of holomorphic one forms is a vector bundle of rank G of a moduli space of curves. So I can have coordinates on curves, and then just the fiber is C to the G. So I can just choose whichever coordinates I want on the fiber, which means choose a basis of holomorphic one forms on a given Riemann surface and perturb it. That's not very exciting. There is a very exciting something you can do. So what you can do is you can take, so let Z1 through Zn be the zeros of omega on X. So suppose my holomorphic one form has a collection of zeros. Then I can try to consider the integrals of the form omega over gamma, where gamma is an arbitrary path in relative homology. Okay, what does this mean? This essentially means that you can take just absolute homology of the surface, which is, of course, z to the power 2g. So these are just closed loops on the surface. But you can also take a path, essentially, that goes from some zi to zj. And of course, there are many choices of such paths, and they all differ by absolute homology cycles. And you're going to integrate omega over such a path. And these are local coordinates, not quite on the Hodge bundle, but on the space where you have prescribed the multiplicities of zeros of a differential. So these are local coordinates on a space which is usually called HGN mu, where mu is a collection of integers that prescribes the multiplicities of zeros of a holomorphic one form. So these are so-called period coordinates. The advantage of using them is that they are complex analytic coordinates, and they're somehow very natural. Another great advantage of using them for Teichmüller dynamics is that the action of GL2R is linear in these coordinates. Because you can see that if I'm changing omega by somehow action by GL2R, the periods are still the same periods between the same points. I don't care about the complex structure on the surface to describe its homology. So you can see that just the action of GL2R and these coordinates are just linear. It's the action of GL2R on a bunch of copies of C. So these are local period coordinates on HG. This is what they are. Okay. So the action of GL2R is linear in period coordinates. So let me maybe write what HG mu is. So this is the space of X and omega. where the divisor of zeros of omega is a sum of mi zi, where mi are integers, and the sum of mi is 2g minus 2 because the holomorphic one form has 2g minus 2 zeros. Okay. So here is a mental exercise. So think about moduli space of curves. It doesn't have any reasonable complex analytic coordinates. I mean, it has many, but there is no easy choice. Think now of the Hodge bundle. So it has, well, I mean, substrata inside it. The strata of differentials was prescribed multiplicities of zeros, but never mind. So these things have reasonable complex analytic coordinates that are somehow very natural, linear with respect to the action, and have some good properties. So can you try to use the coordinates on the Hodge bundle to get the coordinates on the moduli space of curves itself? And this is what Igor and Fancl have done a long time ago. And this is going to be local real analytic coordinates on moduli space of curves with some extra decoration. So let me try to tell you what these are. So this K will be the following. So I'll take a Riemann surface X, and I'll take some points Z1, Zn. These are going to be points on X, and prescribe singular parts of a meromorphic differential at these points. So when I say prescribe singular parts, I have to tell you what this means. So what I mean is that I'm going to consider equivalence classes, if you wish, of meromorphic differentials, where I say that two meromorphic differentials are equivalent if their difference is holomorphic at that point. So this really means, if you wish, you choose whatever local coordinates you decide to choose at a given point, and then you just prescribe the singular part of a differential on these coordinates. Okay. So the space of all such is going to be this MGN K, where K maybe encodes the order of singular parts, whether you have a second order pole, third order pole, 25th order pole, or something like that. Okay, and then for any point X, Z1, Zn, singular parts, there is going to exist a unique differential psi a meromorphic differential on X with the singular parts, and all periods real. Okay. I'm lying a little bit. You have to require, of course, that the residues are going to be purely imaginary if you want all the periods to be real. But then the Riemann's bilinear relations, the non-degeneracy of the Riemann period matrix, tell you that there is going to exist a unique meromorphic differential with prescribed singular parts with all periods real. Indeed, if you have two such, then the difference would have to be holomorphic. But any holomorphic differential with all periods real is automatically zero. So that proves uniqueness. And then for dimension reasons, there must exist such a differential. So then what you can do is you can take the integrals of psi over all loops gamma in homology, well, I have to say more carefully what homology, of X, and this will be local coordinates. So when I say homology, I should really think about homology punctured in the poles relative to the zeros. I don't want to write this down, but basically this still means what you think it would mean, except at the pole, you don't really want to, you want to be able to go around the pole and compute this residue, essentially. That's what this means. And there are going to be more zeros for a meromorphic differential because, you know, each extra pole creates an extra zero. So you can take this period coordinates, if you wish, the periods of a meromorphic differential over all cycles, and this will give you local real analytic coordinates on the moduli space of curves. So why am I putting this on this slide? Because this is somehow a way to use differentials to understand moduli of curves. So yes, this is basically moduli of curves. I mean, I've added the data of singular parts, so let's not worry about it too much. And then on this space, the data of a differential with all periods real, called real normalized differential, gives you some natural choice of local coordinates. And this is something that Igor has observed many years ago, much before Teichmüller dynamics really became a field of study. Okay, so this allows you to consider the so-called absolute period foliation. So what is the absolute period foliation? So let's assume that we're in either of the two contexts. We could either be talking about a stratum of differentials with prescribed multiplicities of zeros, or we could be talking about real normalized differentials. So then we have this large space of homology, and we're computing integrals over this space of homology. But inside it, there is the absolute homology space. As I wrote here, when I'm thinking about relative homology, right? So when we're thinking about relative homology, there is a natural subspace in there, which is the absolute homology. And what this means is that somehow among all the periods, I have a naturally chosen subset of absolute periods, of periods over closed cycles on the Riemann surface. And I can then define a foliation by saying that the leaf of a foliation locally is the space of all Riemann surfaces with a differential, or just Riemann surfaces with singular parts and the real normalized differential, such that the periods of this differential over all absolute homology cycles are constant. So what this means is I'm going to consider inside my moduli space of curves with a differential, the space of curves with a differential, such that the periods of the differential over all 2G absolute homology cycles are fixed. The dimension of the moduli space is higher, so I'll have some freedom. So the freedom will be basically that, you know, the relative periods, the periods between zeros of the differential can change, right? So you somehow imagine you are moving the zeros away, but somehow the absolute period stays the same. So this is a foliation, which is called the absolute period foliation, or the REL foliation, or the isoperiodic foliation, or can be called many other names as well. So this is a foliation on whatever space you're considering here. So either on the space of differentials with prescribed multiplicities of zeros, that gives you an actual foliation. And each leaf of this foliation is complex. The tangent space is complex. The coordinates are the periods. And everything, the transverse direction is also complex. And you can study this foliation, and there is some kind of transfer principle, which basically says, this is due to Calsamiglia, Dirac, and Francavilla, which basically says that the dynamics on the foliation is more or less the same as the dynamics on the space of periods. So somehow for each leaf, you have the space of periods, the set of absolute periods on this leaf, and somehow this, the action of the GL acts on this periods, and this will somehow capture the dynamics flowing on the leaves. I don't want to go in that direction, but it somehow says that in some sense, the absolute period foliation captures much of the dynamics of the system. And if you want to study the Hora cycle flow, so this is a part of the GL2R, then also this foliation will help you. So what I wanted to try to do now, and maybe this is ill-advised, and then I'll regret it in 5 minutes, is I want to try to explain to you in 5 minutes a proof of a theorem of Diaz that Igor and I wrote 10 years ago using this foliation for the case of real normalized differentials. Okay. So this is somehow one proof that I think I'm trying to put in this talk. So I hope that this will be clear. Please do ask questions. Before I go, any questions on how these foliations work or anything else? Or did I lose everybody completely by now? I don't know. It's very hard to tell on Zoom.
Not at least me, Sam. It's okay.
Hmm?
Not at least me. You haven't lost.
Well, I haven't lost you. That's good, Igor. Yes, okay. So maybe it's boring for others. Okay, so let's do this. So here is our setup. So I'm going to consider moduli space of genus G Riemann surfaces with two poles, and then I'm going to consider psi will be a real normalized differential on such a Riemann surface with two simple poles. So the two simple poles will be at these two marked points. So what's the setup? You take a Riemann surface X, you take 2 points in them, point number 1 and point number 2. You consider the space of all meromorphic differentials that have only two simple poles at these 2 points with residue, say, plus I and minus I. Among all such differentials, there exists a unique differential such that all of its periods are real. So this gives me local real analytic coordinates just on the space MG2. I don't have to prescribe any further data of singular parts or whatnot, because the residue is a globally well-defined function. So the theorem that you can prove is the following. It says if Z is a complete subvariety of MG, is a compact subvariety, then dimension Z is at most G minus 2. Okay. So instead of proving this, Igor and I prove basically the bound for complete subvarieties of MG2, except you should allow the 2 points to coincide, but ignore that. So let me try to draw a picture. So here is my space MG2, and here is my foliation. And let's say here is my compact subvariety. Then I can consider the intersection of this subvariety with the leaf of this foliation. So this is Z. This is a leaf L. So Z intersect L. What is this? So the foliation that we have, in this case, the leaves are complex. So local coordinates on the leaf are the integrals of the differential from one of its zeros to another. So these are complex numbers. So the leaf is complex. The transverse direction to the leaves is not complex. That's what makes the foliation real analytic. If you now look at the real normalized differential, then the imaginary part of the integral of this differential from one point to another is globally well defined, because all the absolute periods are real. So the imaginary part of an integral from one zero to another is completely insensitive to any choice. So what this means is that this is just a globally well-defined function of the moduli space. And if I restrict it to L, it's a harmonic function. So thus, and I'm cheating here, but essentially that's true, this means this imaginary part of this period restricted to the intersection of a complex, sorry, when I say subvariety, I'm being in algebraic geometry, it's a complex subvariety. So the intersection of Z and L is a compact complex subvariety. That's not quite true, you have to do it carefully. You would think that this is compact, and then this must be constant. because it's a harmonic function on a compact complex space, so it's constant. But then, if such a function is constant, the real part of this same integral, which is now a multi-valued function, is also constant. But you see, this of course means that the integral from Zi to Zj of the differential is constant on such an intersection. But the set of all such integrals gives local coordinates. On the leaf, right? Because the period coordinates are just to say that you can take the integrals of the differential over all paths on a Riemann surface in relative homology. So you take all absolute periods and all relative periods. This gives you local coordinates. A leaf means you have fixed the absolute periods to be just constant. So the relative periods give you local coordinates on the leaf. So this means that Z intersect leaf is just a point, because the local coordinates are all constant. So if you have a space, all coordinates are constant. This means you're talking about a point. But if that's the case, then this is to say that the dimension of Z is at most G, because this is a codimension of the leaf, the moduli space. And that's precisely the theorem of Diaz. And I've cheated here in some significant ways, but conceptually, that's how the proof goes. The significant cheat here was that if I have a compact subvariety of the moduli space and I intersect it with a leaf, which is everywhere dense, potential, and horrible, the intersection is not going to be compact. So I cannot just say that. So I really have to say that the periods are globally well-defined functions. So I'm going to take the maximum over the whole space, and I'm going to take a leaf through that point, and then I'll do a local computation there. But other than that, the proof is correct. So what's the message of that? Well, one is that Igor had a great idea to consider real normalized differentials. The second message is here there is one way that differentials on Riemann surfaces were used to study a question that has nothing to do with differentials from the start. It's a question about the geometry of the moduli space of curves. And if you look at the statement of the theorem, it says if you have a compact complex subvariety of the moduli of curves, then you can bound its dimension. And that has nothing to do with differentials. Yet somehow, using the extra data of a differential on the Riemann surface allows you to get more information in this situation. Okay. The original proof of the theorem.
Sorry, may I ask a question?
Yeah, sure. Yes, Zhenya? Yes?
Does there exist a G-dimensional Z from your proof? So is there bound sharp?
No, we don't know. So that's completely unknown. So this bound of Diaz, I mean, this G that we have is related to the G minus 2 on MG, so it's really the same. And then you can ask, what is the actual maximal dimension of a compact complex subvariety of MG? And embarrassingly, the best bound is this bound. So the best bound is that the dimension is at most G minus 2. If you try to construct complete subvarieties, the maximal dimension of a complete subvariety that people know how to construct is log G, I mean, log base 2 plus 1 or something like that. So, for example, if you ask about the maximal dimension of a complete subvariety of M4, this is already not known. So in M4, we know how to construct a complete compact complex curve, but it is not known whether M4 contains a complete surface. And then it gets even more embarrassing if you increase the genus. So our proof, I mean, tells you that if such a subvariety were to exist, it would have to intersect all the leaves transversely. But it doesn't tell you how to construct such a subvariety. So the answer is not known. Did I answer your question? Okay, so the best I can see, Jenny is frozen, so let's assume I have answered the question. Okay, well, let's go to the next question, perhaps. So this is one direction. The second direction I wanted to discuss is understanding limits of differentials. So let me try to explain the difficulty here. And this is about compactifying this stratum, so H212. So what does this mean? This means I want to consider a Riemann surface X and M2, I'm sorry. And I want a differential form omega such that the divisor of omega is just 2 times some point. So it means the form omega just is a holomorphic one form that has just one double zero at one point. Of course, I secretly know that this is just a set of Weierstrass points on hyperelliptic genus 2 curves. Every genus 2 curve is hyperelliptic and whatnot. But I'd like to try to understand how this gets compactified. So think about the compactification. So here is a nodal genus 2 Riemann surface. Let's assume that my point P in the limit is here. So this is a nodal Riemann surface where I have two components, one component of genus 1, the other component also of genus 1. And I want to know what is the limit of the form omega here. So maybe it's the form omega 1 here and the form omega 2 here. You know that the limits of holomorphic forms on nodal surfaces can have at most a simple pole at the node here. However, this is a separating node, so you cannot have a simple pole because the sum of the residues must be 0. So omega 1 and omega 2, I mean, this is the two parts of the limit, are both holomorphic. And omega 2 must have a double zero at the point P. So what did the formula say? I said the following. I'm trying to compactify a stratum of holomorphic differentials on genus 2 curves with one double zero. And I'm looking at what happens over the boundary point where the nodal surface has two genus 1 components and the marked point is on one of them. Then in the limit, the form must still vanish with multiplicity 2 at the marked point. But then the limit is a holomorphic form. So the only way a holomorphic form can vanish on a genus 1 Riemann surface is if it is exactly equal to 0. So the main difficulty is in the limit, the differential becomes identically 0 on some irreducible components of the stable curve. Okay, and if you think about this, what this means is that you lose a lot of information. So somehow on one of the components of this curve, on this component here, omega 2 is just identically 0. But if it's identically 0, I no longer know which point is P. Is it this point? Is it that point? Is it that point? Somehow the information on the geometry of P is completely, on the geometry of that component is lost. If my differential in the limit is just identically 0, I've lost all control I may have had otherwise on the geometry of that component. So I know nothing. So the idea is the idea in algebraic geometry that has been around for a while, but has never been completed, is the idea of limit linear series. So you take a family of Riemann surfaces. I mean, smooth Riemann surfaces, X degenerating to some nodal Riemann surface Y, and you're going to rescale the differentials in such a way that the limit, and so you'll take Riemann surfaces X, maybe they're called XT, because the family with parameter T, maybe the forms are called omega T, and you want to rescale, so you will rescale by some function f of t in such a way that the limit of f of t, omega t, is not identically 0 and exists on a given component of y. So what this means is that somehow in my example above, what happened is I had two components, and on one of them, the limit automatically becomes identically 0. So you look here, on the component on the right, the limit of the differential is identically 0. On the left, the limit is not identically 0. So this means that somehow I don't need to rescale anything to get a reasonable limit on the left component. But if I want to get a reasonable limit on the right component, I have to take the family of differentials and I have to rescale it so that it doesn't go to 0 anymore. Okay? And then if I do that, what I'll get on the right component is some non-identically 0 differential, which, however, will have a pole at the node. Because somehow this is where it attached to another component where the limit was already non-zero before I rescaled. So this is the idea of limit linear series. It works reasonably well. It works remarkably well for the example I just did above, so you can do it all very, very quickly. The reason it works so well is because the example I had above is a curve of so-called compact type. So there is no loop in the dual graph. Or if you wish, the Jacobian of this curve is still compact. So limit linear series were developed 30-something years ago, and they have been developed in full generality and are extremely successful at dealing with all sorts of questions for curves of compact type. But they just don't work for curves not of compact type. There has been work since, but somehow there has been no definitive answer. So what happens for curves not of compact type is somehow when you try rescale and you start running in circles because maybe you have two components of the nodal curve that map it, that intersect in two nodes, and you somehow start scaling, and it somehow tells you to start scaling in a loop, and that somehow doesn't work so well. So for moduli of differentials, however, you can compactify it in a better way. So theorem, this is with Matt Bainbridge, Dawei Chen, Contage and Roux, and Martin Mueller, is that there exists a good compactification that we denote this way of the stratum of differentials. Okay. And not just that there exists, of course, we construct it. So what does good mean? So this is a compactification, which we call the moduli space of multi-scale differentials, which compactifies the moduli space of differentials with prescribed zeros. Recall that this is a moduli space of x omega, x maybe points z1, zn omega, where x omega is a point in the Hodge bundle, z1, zn points on x, and the divisor of omega is the sum of mi zi, which is to say the differential has zeros at the point zi precisely of where this mi. And so by a good compactification, we mean that this is a Deligne-Mumford stack, it's smooth, it has a universal family, the boundary is normal crossing, it maps to mg bar. So it's basically almost as good as the Deligne-Mumford compactification of the moduli space of curves. I'm not even going to try to go into the details of that, and I know that a couple of people in the audience, notably, with my apologies, Igor, have heard this. But basically, the idea somehow is to make the limit linear series work. You somehow rescale the differentials and the limit in a good way. And if you rescale this and keep track of what you get on every component, you get more and more structure on the nodal Riemann surface on the stable curve. And that's what you're going to use. So this is a compactification with a moduli space of differentials. It's a space that has all the nice properties you really want the compactification to have.
Sam,
So this, yes?
what is the difference between this compactification and just the closure of the stratum inside the space of holomorphic differentials?
Excellent question. So, okay, so let's call this theorem 2 if you don't mind. So theorem 1, the same authors, B, C, G, G, M. So the theorem 1 is the following: the closure of the stratum of differentials in the total space of the Hodge bundle. So you take MGN bar, the Deligne-Morphic compactification of MGN. The Hodge bundle extends. I'm pretending that whereas in the holomorphic case, I can say the same in the meromorphic case. So I take the stratum of differentials, and I can take its closure in the Hodge bundle. And the first theorem we can do is we can describe this closure. So there is a bunch of conditions, which I'm not going to write here, but it basically says everything works out well with limit linear series, even though it's not phrased in this question. So we can describe this closure. What is not written in that paper so well is, however, this closure, let's call it HGN mu bar, is, I'm tempted to say arbitrarily singular, but that's not true. It's very singular. Basically, it has arbitrary toric singularities. It's non-normal. It's very singular. Has no reasonable universal family. Well, I cannot say has no reasonable. I cannot prove a theorem it doesn't have a universal family, but there is no natural universal family you can put in it. So what this says is that if you just take the closure of the stratum of differentials in the total space of the Hodge bundle, this is going to be horribly singular. So basically, you can construct essentially by hand, essentially any toric singularity you can have, which is bad news for any kinds of questions. I mean, the singularities are not canonical. The intersection theory is undefined. It's not so good. And there is no reasonable universal family. The compactification in theorem 2 is a good compactification. It's a smooth stack which has a universal property. This compactification, and this beta compactification, does map to the closure. Also, that's part of the good properties. So it maps really not to the closure, but to the normalization of the closure, really. So this is why this compactification is better and requires more work. Did I answer your question?
In a sense, yes, but in particular, you mean that this closure is normal, since it's
No, the closure is not normal.
not normal, but it
The closure is not normal.
it needs a normalization.
So you normal. So of course, when I take the closure somewhere, but it's not normal. When you take the normalization no longer sits, of course, inside the compactification of the Hodge bundle.
But how can it happen that it does not have a universal family? Because since the general stratum has a universal family, and
yes, there is no reasonable way to extend it. So you see a point on the compactification. If you just look at the, so the point is, if you look at the point on the boundary sits on the compactified Hodge bundle. There is a point on the boundary of the closure. But all this means is that your differential is identically zero on a number of components. And somehow, if you declare that your universal family consists of differentials that are identically zero, you have just lost much of the information, and you will not be able to recover this. So you've forgotten too much. So somehow you need to record that even though the differential is zero, somehow if you rescaled it, it wouldn't have been zero. And then you need to record what it would have been if you rescaled it. And that's the information you're losing. So sort of that's the information you need to record. And the good compactification records this information of sort of the limit linear series kind of limit of a differential. So it records on each component the non-identically zero meromorphic differential that would have been the limit. It also records more data. It records somehow how to open this up. It records some, in some sense, infinitesimal data of how to open up every node with a differential at this node. That goes beyond what I meant to say in the remaining 2 minutes.
Okay, thanks.
Make sense?
Yeah, it makes sense. I have to think the subject out.
I'm happy to discuss this further. Okay, so that's one work, but there is a still more precise result, which is due to Igor, Haya Norton, myself. The more precise result is for real normalized differentials. So the limit of a real normalized differential in a degenerating family of Riemann surfaces is determined explicitly. Okay. When I say limit, I don't really mean limit. I mean the what I would call scaled limit or something like that, rescaled maybe limit. So this is to say that on every component of the curve, you don't just have a zero maybe identically, but you have rescaled so the limit is non-zero. And when I say explicitly, this means on every component of the nodal curve, we can determine, given a degenerating family, the singular parts at all the nodes. So what does this mean? So the limit, this rescaled limit of a differential under degeneration, this is a picture that emerges, is going to be a collection of meromorphic differentials on the components of the nodal curve, satisfying some conditions. And particularly at the nodes, they will have some higher order poles, because if I have rescaled one component but not the other, somehow I'll pick up a pole. And the description of the complexification that was on the previous page said, well, basically there should be a pole. But the result we have with Igor and Hai is much more precise. It's for the context of real normalized differentials, but in principle, it works just as well in any other degeneration families of differentials. It tells you not just that you will have a node, a pole at a node, but it tells you precisely what the singular part of the differential will be in a given family. So this is much more detailed information, which we have used to describe very explicitly the limits of real normalized differentials, but when it can be used in much more generality as well. Okay, so I know I should wrap up. So I wanted to say something about potential further directions where one could try to think of applying degeneration techniques for curves and differentials. And this is in no particular order, and there are many other things. This is just my idiosyncratic list. So you can think about Weierstrass gap sequences. This is a sort of classical problem in algebraic geometry. So if you have a curve, you have Weierstrass points. The Weierstrass points are the points where you have a function with an unexpectedly high order of zeros, something like that. You can phrase it carefully. And then you can say that there is a Weierstrass gap sequence. So you take a point and you ask whether there exists a point with a function which has a double zero there, a third, and so on. And so you'll miss a bunch of such functions, and this is a gap sequence. So the question is, what Weierstrass gap sequences occur in genus G? And that question is still open. So there are some partial results, of course, classical and less classical. But if you want to ask a question as full generality, it's not known. So if you have a generic curve of genus 100, if you have curves of genus 100, all curves, the moduli space of all curves of genus 100, and you ask what are the possible Weierstrass gap sequences, nobody knows. So there are some restrictions, there are some constructions. And the method of doing this is, again, often by degeneration. How is that related to differentials? Well, Weierstrass gap sequences are about functions or about differentials, if you wish. So if I think about this as a question about differentials, this is a question about a collection of differentials, whether there exists a collection of differentials on the Riemann surface such that they have zeros at a given point with prescribed collection of multiplicities, essentially. And so what this means is if one can somehow upgrade the techniques developed so far, which are developed for understanding the degenerations of one differential on the Riemann surface under degeneration, to understanding the degeneration of a collection of differentials, one could have a degeneration technique to handle that. And that's an open problem. I have nothing to say here. I have no idea how to approach it, but I don't think anybody has tried. And that would be nice because somehow this area has been dormant for a long time and there has been no progress. Another question is classification of orbit closures in Teichmüller dynamics. So if you have in Teichmüller dynamics an orbit closure, it will never be compact. It will always hit the boundary. And then you can try to say, okay, so I have an orbit closure, which by fundamental results of Eskin, Mirzahani, Mohammadi, and Philip is an algebraic variety, which is given by linear affine equations and period coordinates, which I described. You can ask what is its boundary. And we have some results with my student Fred Benirschke and Ben Dozier, and so on, is we somehow we get some information, and it would take me half an hour to try to set this up carefully, get some information on sort of defining equations of an orbit closure from knowing what its boundary looks like, what its boundary looks like. So what do I mean by that? So suppose you have an orbit closure which you know contains a Riemann surface of a given kind of degeneration with some prescribed extra data that you need to understand the multi-scale differential in such a limit. If that is the case, then we can deduce that, for example, if you have two nodes on your Riemann surface that are somehow at the same level at the limit, which is to say that the differentials goes to zero at the same rate around these nodes, then we know that the residues around these two nodes are just proportional on this orbit closure, which is some kind of information on what the defining equations of orbit closures will be. And we get much more, and we reprove some theorems from Teichmüller dynamics that have a proof from flat surfaces and so on. So that's the kind of information we get. And there is much more, and you can try to use these degeneration techniques to prove more results, to prove reprove algebraicity of orbit closures and so on. That's another direction. Another direction is to try to understand birational geometry of subvarieties of moduli spaces. So there is, for example, a classical question. So this is the so-called minimal stratum H2G minus 2. Sorry, I apologize. HG1 2G minus 2. So again, this means X omega. So X is an MG, and the divisor, there is a point Z, and the divisor of omega is 2G minus 2 times Z. Z is in X. So this is to say that you have a holomorphic one form on the Riemann surface with maximal multiplicity 0 at one point. And it could be that this is a hypoelliptic curve, but let's consider the case when the curves are non-hypoelliptic. So this is a so-called locus of subcanonical points, if you wish. So this is a subvariety of MG1 of codimension G minus 1, I think. I may be slightly off. Sorry, I'm always confused. I should have computed the number beforehand. Again, I have to projectivize, there is points, never mind. So that's a subvariety. And you can ask, is this affine, for example?
Codimension is 2G minus 1.
Hmm?
Codimension 2G minus 1.
No.
Why?
No.
This is
No, I mean, the dimension of this thing is the same as the dimension of the hyperelliptic locus. So it's roughly G. So we're talking, Igor, think about it this way.
Codimension in the Hodge bundle or in the module space?
Of codimension G minus 1 in the moduli space. Okay, in the Hodge bundle, it has codimension roughly to G plus a constant. In MG, it's just G. So it has the same dimension as the moduli space of hyperelliptic curves. The moduli of hyperelliptic curves has codimension G minus 2. I'm confused about ones because I have to projectivize somewhere. So is this affine? It's somehow an interesting question. There is a more general question of what is the geometry of the strata of curves with H, G, and mu when considered as subvarieties of MGN. Are they affine? Are they far from affine? What is their homology? What can you say here? And this is somehow a well-known open question. And again, you can imagine doing this by degeneration techniques, maybe combining them with the techniques of real normalized differentials, but I have no idea how to do it. And one last question that somewhat embarrassingly, Igor and I haven't yet solved is the number of cusps of plane curves. So the question is, what is the maximal number of cusps of a plane curve of degree D? So what this means, if you have a curve C in P2, degree D, and you can ask what is the maximal number of cusps it can have. And the way it's related to all of the above is, suppose this P2 has coordinates X and Y, non-homogeneous. Then you can consider the differentials dx and dy is meromorphic real normalized differentials on C. Of course, they're real normalized because they're exact, all their periods are 0. But you can think of this as more generality. And this is what Igor and I have been meaning and trying to approach for a while now. And as part of the birthday wish for Igor, I just hope that soon, or before the next birthday, or before some birthday soon, this will not be a direction for future research, but will be a nice paper. So this is another direction where you can imagine applying the generation techniques for differentials. Okay, well, that's all I wanted to say. Thank you. Thank you.
Спасибо.
Thank you.
Thanks, Sam, for a nice talk. Before I'll ask the usual question about any comments, remarks on the talk, I just want to say thanks for coming, all of you, and sorry for the fact that the conference was planned for this day was canceled relatively recently. It was canceled so recently because there still was a hope that might some miracle happen and you will be able to come here. Still, as Sam had in future, I hope you will all come at some moment to Skopje and we will see each other in person because it has a different flavor of meeting than just in Zoom space. Thank you. Now, returning to a role of chairperson. Any comments, remarks? Okay, then thanks again, and see you in the future.
Thank you.
Thank you.
Thank you, Sam.
That was really nice talk.
Yeah, it was very nice.
The problem is that our hope to solve the problem with cusp is so long, so that is, I still don't know. Is it reason to believe that it's true or just?
Of course, it's reasonable to believe, Igor. You know, otherwise.
Yeah, actually, you see, the problem is that everything is ready to prove the bound we aim for. Just one little step. The initial. Sorry.
What is the bound?
The bound.
3/10 of d squared.
In front of d squared.
3/10 of d squared. Let me write it now.
Yeah, but Enrico, the problem is it's 3/10 of d squared plus some lower order terms. And if I happen to write the wrong lower order term, we will just have proven the Bogomolov-Miyake-Yau inequality for surfaces not of general type, which is false. Which is how we discovered the mistake in our first approach. And that's not so good.
I see.
But you
so
see,
it seems that it's related to other things. Sorry.
Enrico, the lower bound is, which is known 0.29 plus something, very, very close. And the best known upper bound is also in the limits of 0.01 or something like that.
So tell me again, what is not the lower bound?
There are two. Lower bound is by construction of such curves, and it is 0.29, roughly speaking, d squared.
Okay.
The upper bound, first, the best was by Hirzebruch, then it was improved by
well, the best result is by Adrian Langer at the moment, by using logarithmic Bogomolov-Miyake-Yau inequalities for surfaces.
So the upper bound is 0.309 d squared. Our conjecture is just in between. And so it's close to be proven, but again, the induction is proven, the initial step is missing, that's all. But it's for so long that I actually don't know what to think. Okay, thank you again.
Okay, thank you. Thank you, Sam. Happy birthday, Igor.